what I want to talk about is what are the impacts on the natural world, and particularly on the living natural world. It's a subject that I've focused on for 23 years, done 2 books on. First book, 1992, was just about what might happen. By the time the second one was out in 2005, things were already changing. So the whole notion of the greenhouse effect came from the Swedish scientist Arrhenius, because he asked the question, why is the Earth a habitable temperature for humans and other forms of life? It's also old science because he did that in 1896. If you look at the temperature of the Earth over the past 120,000 years, you see 2 things very clearly. One is that abrupt climate change is the normal state, despite the fact that our models are linear and gradual. And more important, the last 10,000 years is an unusually stable period in terms of the global climate. And that includes all human recorded history. It includes the origins of agriculture, the origins of human settlements. It makes altogether the point that the entire human enterprise is based on the assumption of a stable climate, which is why, of course, we talk so much about the weather. John has sort of dealt with all of this. We are way beyond CO2 levels of the last 600,000 years. The temperature of the Earth is responding. We're 3/4 of a degree warmer than in pre-industrial times. And because of lags in the system, even if we stopped emissions today, we're due for another 3/4 of a degree increase. So what is happening in the natural world? Some of it has been touched on by John, the physical changes in the natural world, particularly around the phase change of the solid to liquid state of water. So lakes are freezing later in the year, ice breaking up earlier in the spring. Glaciers are in retreat all over the world. Glacier Park will soon be that only in name. And this is not just a matter of sort of scenery and protected areas. This is the source of watersheds and water supplies for the capital of Bolivia, the capital of Ecuador, important to the origins of the great rivers in Tibet, of China, and even to maintaining the Ganges as a year-round flowing river. All tropical glaciers are retreating at a rate that they will be gone in about 12 years. So if Hemingway were writing his short story today, he would have to choose a new title. And of course, we have this dramatic change in ice in the Arctic Ocean. John has covered this, but this movie function makes it even more dramatic. See the expansion and retreat of the ice every year, and that it is an accelerating function. In addition, glaciers are on the move in Greenland. They create their own sort of seismic activity, much more, as you see in recent years, in the warmer months of the year, but more disturbing at an increasing rate year by year. Sea level is rising, of course, primarily so far through the thermal expansion of water. And it is already affecting some of our protected areas in the United States. Blackwater National Refuge is basically disappearing below the rising Chesapeake Bay through sea level rise and subsidence. It will soon be just a marine refuge. There are more intense storm functions, whether tropical cyclones are still debated or not. We are having more intense weather events generally. And of course, because the summers are warmer and the snows are melting earlier, we have the increased wildfire in the Western U.S. So what is the biological underpinnings of the world of responding? How is it responding? Basically, a lot of organisms are changing the timing in their annual cycles, so lilacs are blooming earlier in New England. Many flowering species are blooming earlier at the Royal Botanic Gardens at Kew in London. And it's not just animals, it's also plants. So many species of birds are nesting earlier, migrating earlier, laying eggs earlier. One has even ceased to migrate. Some mammals are ending hibernation earlier. And species are changing where they occur. This is one of the best known butterfly species in North America, and it is clearly moving upslope and northward in its distribution. And the National Arbor Day Foundation, which one could hardly accuse of being an environmental terrorist extremist organization, it's just about people who love to plant trees, found it necessary to produce a revised version of their hardiness zone map, which is the guide to which species of trees you can expect to be successful with where you live. There's a developing body of knowledge about the health risks for humans from global warming. My point of including it here is that sooner or later we will see those same things in wild plants and animals. And this unreadable slide is here to make the point that we are long beyond the point of this being individual anecdotal examples. It is now statistically robust. Nature is on the move in response to climate change. It's not just on the land, it's also in the oceans. Fish species and plankton species are changing their distributions. And in the Chesapeake Bay, the biologically rich eelgrass communities turn out to have a very sensitive upper temperature limit for the eelgrass itself. So the southern boundary of eelgrass in the Chesapeake Bay has been marching northward steadily year after year. This is a problem not just in the temperate zone and in the polar regions, it's also reaching down into the tropics. This is the legendary Monteverde cloud forest. Cloud forests get 98% of their water from clouds through condensation. And what has been happening there is that the level of cloud formation has been moving up in altitude. So Monteverde has more dry days during the year, not a good thing for a cloud forest. And it is thought that the first species to go to extinction because of climate change is this golden toad from Monteverde. Whether you accept the golden toad as the first example or not, there are plenty of other changes occurring in Monteverde as species move upslope from the dry tropical forest below. And in the oceans, the rainforest equivalent, the coral reefs, wonderful, highly diverse, highly productive, technicolor world, basically all look like this when I was a graduate student. You can go anywhere in the world and look at a coral reef, and it would be this wonderful, brilliant, lively community. It turns out that tropical coral reefs are very sensitive to climate change because it affects the basic partnership which is at the basis of coral reefs. It's a partnership between a coral animal and an alga, and with only a couple degrees increase in temperature, the coral animal ejects its alga partner, and you get the whole technicolor world going to black and white in what are known as bleaching events, and most of the diversity of the reef plunges. And of course, there are dramatic examples of species dependent on ice. In the Arctic region, the polar bear is the poster child, but I would merely make the point that there are dozens and dozens of species up there, the natural histories of which depend on access to the ice. So those are very minor ripples that have occurred so far, just slight adjustments by nature, but clearly happening all over the place. The real issue is, what does it look like looking ahead? First attempt to do that was this paper in Nature, the first issue of January 2004, estimated that double pre-industrial levels could lead to the loss of 20 to 30% of all species on Earth, a number which the IPCC confirmed this last year. And of course, when you think about it, it's not just about temperature change, it's also about moisture change. Temperature and moisture are the two most important things for terrestrial organisms. Temperature and pH, the two most important for aquatic organisms. We're already seeing a drying trend in the Middle West affecting the very important prairie pothole ecosystems which support the central flyway. This year obviously is an exception to that, but the overall trend is drying. We can anticipate that there will be lots of examples in which two articulated species in terms of their biology will be driven apart because one will be dependent on day length cues and the other on temperature cues. That could be the case here with migratory shorebirds, which have a day length cue for their migration, and their major refueling stop, namely feeding on the eggs of horseshoe crabs in Delaware Bay, is much more likely to be driven by temperature as well as phases of the moon. The kinds of decouplings we're seeing so far are mostly around the phase change from ice to water, but soon we're going to see many biological ones. One can look ahead and see what it might be like for particular species. The sugar maple is so important in northern New England in many ways. Basically, according to all 5 major computer models, will become only a Canadian species with double pre-industrial levels of CO2. So if you want maple sugar, maple syrup, and autumn foliage, you'll have to go to Canada. It will affect freshwater systems, particularly cold water species like trout. This is what caught John Warner's attention as a fly fisherman. And there will be interesting complex interactions like this between an alien beetle species, the emerald ash borer, and the American ash, where essentially the summer is now effectively longer. The beetle gets in one more generation, tipping the balance in favor of the beetle against the American ash and the American icon it supplies, namely the baseball bat. High altitude species like this little pika will move upslope in response to climate change, but at a certain point there will be no further upslope to go. So high altitude species will be in peril. Species along coastlines obviously will be at risk from sea level rise, and in particular, species on low-lying islands will eventually have a point where there is no further they can go either. So those two groups of species are particularly vulnerable. And of course, bleaching events will become much more frequent for coral reefs, so the outlook for tropical coral reefs is pretty bleak indeed. One could look at what will happen with individual species and see, in this case, a future for this particular flowering plant in South Africa. But there are many, many little bits of that story that one could put together. More important, there are about 3 or 4 very serious complications as we look ahead. Climate change is not new in the history of this planet and life on Earth. Glaciers came and went. We did not lose a lot of species in the process in North America and Europe, but the big difference today is that as the individual species try to track their required climatic conditions, they're going to do it in a landscape unlike the Adirondack Park, a highly fragmented landscape, which basically will be an obstacle course to their ability to disperse. As Michael Robinson, the director of the National Zoo, once said, the species would move, but Philadelphia will be in the way. One can deal with that particular problem pretty easily in terms of a policy prescription by putting natural connections back into the landscape. The next complication is much more difficult to deal with. And we know that it's the individual species that respond to climate change, each in their own direction and at their own rate. It's not the biological communities that move as a unit, it's the species. So this is what happened with 6 species in Europe after the last retreat of the glacier: 3 mammals, 2 trees, and 1 insect. You can see they all went in different patterns. Basically what this means is the individual species will move individualistically, and the ecosystems as we know them will disassemble, and the surviving species will reassemble into new ecosystems hard for us to actually even predict. There's also the certainty that change will not be linear or gradual. We know that's true of the climate system. We know the global conveyor belt, which is so important in terms of distributing heat around the globe, has faltered in the past. But more importantly, right now, we are already seeing threshold changes in ecosystems. In the coniferous forests of southern Alaska, British Columbia, Colorado, Scandinavia, and Germany, we essentially have a situation in which a native pine bark beetle is able to get in 1 more generation a year, tipping the balance in favor of the beetle and leading to massive tree mortality in those particular regions. Some tens of millions of acres of forests are being so affected. See a little time sequence here in British Columbia, at the start of which you see minor outbreaks of the beetle, and then it is sort of pushed back by a cold winter. But as time goes on, the summers are warmer and longer. The beetle is able to get a greater foothold. Cold winter in 1986 knocks it back, but not for long. And progressively the beetle gets the upper hand. So literally there are places today in those regions where 70% of the trees are dead. Major timber management problem and a major fire management problem. On top of that, we need to be concerned about system change. And this is one of the more interesting ones John was referring to. This shows the generation and distribution of moisture around the world, and as you look at that slide, you see that moisture comes in off the Atlantic and gets into the Amazon basin and then is recycled as it goes across the basin. In 2005, that system broke down, probably in a preview of what climate change will bring, the greatest recorded drought in the history of the Amazon. And all the computer models show some response of that sort. So at the moment it is projected at about 2.5 degrees global temperature increase over pre-industrial. You'll have massive Amazon dieback. So a lot of carbon will go into the atmosphere as a consequence, and a lot of biodiversity, of course, would be seriously affected. One of the big surprises in terms of system change in the last few years is that the oceans are becoming more acid. It's not temperature, it is not precipitation that's causing this. It's the simple greater concentration of CO2 in the atmosphere. Many of us have been so relieved the oceans were taking up so much of CO2 and overlooking the fact that a certain portion of it was being turned into carbonic acid. So the oceans today are 1/10 of a pH unit more acid, Doesn't sound like much, but it's a logarithmic scale. That means 30% more acid. And it will be a matter of great consequence for the tens of thousands of species in the oceans that build their skeletons and shells from calcium carbonate. They use an equilibrium which is both temperature and pH dependent, and it will affect not only the kinds of organisms we all know about, but also tiny little ones which exist in untold numbers and are at the base of food chains. We're already seeing changes at the base of the food chain off Alaska and in the North Atlantic, and one could literally get to a point where an organism like this little pteropod could have its shell go back into solution while it was still alive. Other worries of system change involve sort of the warming in the boreal regions, release of methane, and other things. And we know all of this will relate in some ways to critical thresholds in the Earth system. We know there are such thresholds. We don't understand a lot about them, but clearly, if we get to this point, we're playing with stuff which we have no business playing with. So the big issue then is, what can you do about it? Two big categories of things to do. One is revise conservation strategies, which we're not particularly here to talk about, and the other is to look at the ways to change the energy base and the release of greenhouse gases and their increase in the atmosphere. So I will skip over those, just make the point that there is a major adaptation challenge for natural resource management in the United States and around the globe. And I'm going to go ahead to 2 or 3 final slides. One is, you may hear people say, why did you make us set up all those protected areas and spend all that money when the species that we set them up to protect won't be able to live there anymore? That's exactly the wrong way to think about it. Protected areas that we have today are the safe havens from which these species will be able to move and track their future required conditions. We basically need more conservation, not less. And of course, there is a big plus from the conservation point of view in the tropical deforestation component of greenhouse gas increase, which makes Indonesia the 3rd largest emitter and Brazil the 4th largest emitter. We need to use the power of biology in addressing the greenhouse gas issue, as well as work on the energy side. It's 1 out of 5 molecules of CO2 come from this source. Coming to a solution for this is good for the forest, it's good for the biodiversity, it is good for the climate. And finally, I will leave you with this graph from the IPCC synthesis report. Temperature increase on the vertical scale on the left, consequences kicking in at various temperature levels on the right. The red is the increase we've experienced so far. That's to about 3/4 of a degree. As I said, we have another 3/4 of a degree basically already in the can. That takes us to 1.5 degrees. John mentioned that 2.0 was a level that people thought would be safe. Certainly, some of the first people coming up with 2.0 did it from thinking about the state of ecosystems. I would suggest that if we're already seeing threshold changes in ecosystems and already seeing system change like ocean acidification, that's a very conservative way to look at it. We're likely to see serious disruption before then, and that's only 0.5 degree beyond where we are currently headed. And just 0.5 degree beyond that is where you get Amazon dieback. So the point here is that this issue is even more urgent than most people appreciate, and it makes this conference even more timely. Thank you very much.